Are you able to see the screen here?
Yes, sir.
Okay, so I think in the last class we had discussed the remaining parts, right? We had discussed these parts, selection of transducers, and then the errors, and then I had explained you the potentiometer, the resistor type, and along with that I had explained you the inductor and capacitor, I think, right? ये explain किया है ना last class में.
Yes, sir.
Today let us start with the LVDT. Okay, so on the screen you can clearly see that this is the normal construction. Actually the image is not that much clear, but I think it is somewhat clear for understanding. Okay, so you can see on the screen this is our LVDT construction. Okay, so I just want to explain you what is LVDT. Okay, so LVDT is normally used for, if there is any issue in my voice then please let me know. Okay, so I think the LVDT is normally used for displacement measurement, and also it is a one type of transducer, right? So this LVDT will be used for converting the displacement into electrical signal, and sometimes this is also used for measuring the pressure also, right? So let us see how the LVDT is going to work. So coming on to the LVDT, so LVDT in the name itself represents the linear variable differential transformer, right? So here you must have a differential transformer here, then only you can able to understand the LVDT. So you can see here clearly, here you can see that here we are having the primary and secondary windings, the one that I am making round. Okay, so here you can see that this is my primary winding and these two are my secondary winding. Okay, and the middle one here, the box, the black colored box, this is my movable core. Okay, and you can clearly see here my this movable core has been connected to an diaphragm, right? So the diaphragm is nothing but an this is going to be moved. Okay, so here the displacement is going to happen whenever this diaphragm is going to move. So this diaphragm is going to move my core, and when my core moves, so what happens, my output voltage will get varied. So how it is getting happen. Okay, so for understanding this you have to understand how the transformer used to work. Okay, so normally I am trying to draw here. So this is my primary winding, and sorry, so normally what happens with the transformer? So normally the transformer is going to have the primary and secondary windings, right? So when and what happens whenever you are going to have the two different windings, and if you place a magnetic material in between them, okay, that means you are going to take the primary and secondary winding, and then you are going to place a magnetic material between them, and whenever you are going to excite this, excite means you are going to give some supply to this primary winding, then what happens, so this primary winding, the winding itself acts as a coil, right? So remember one thing, whenever you are going to discuss about the transformer, the winding will act as a magnetic coil. Okay, so whenever you are going to give some supply, or you can consider it as a voltage. Okay, whenever you are going to give some voltage to the primary winding, so what it will do, so because of the current flowing through the coils, the magnetic flux will come out. Okay, that means your primary winding, or you can call it as a primary coil, so this particular primary coil is going to emit the magnetic field out. Okay, and after that this magnetic field will travel via this core. Okay, that's why initially I had mentioned this particular core as my magnetic core. Okay, the reason why I had mentioned this as my magnetic core is because this is capable of transferring the magnetic flux here. Okay, so you have to understand that because this is capable of transferring the magnetic flux. So whenever you are going to excite the primary winding, what happens, the primary winding when excites, it will emit the magnetic flux, and this magnetic flux will travel via this magnetic core, and then it will link with the secondary winding here. Okay, so the voltage will get induced in the secondary winding. That means you are giving voltage here, and this voltage is converting into magnetic field, and this magnetic flux is getting traveled via this core, and then it is getting linked with the secondary winding, and whenever it gets linked with the secondary winding, so EMF will get induced here. Okay, so it is a big principle behind that, that is the Faraday's law. Because of the Faraday's law, the EMF is going to induce, and we don't need to study the law everything. So what the thing that we need to study is, whenever we are going to excite the primary winding in the transformer, the magnetic flux will travel via core and gets linked with the secondary winding. Okay, the source of the magnetic flux here will be the primary winding, right? So we had excited this primary winding, and because of exciting this primary winding, what happens, this is going to emit the magnetic flux, and this magnetic flux is traveling via this magnetic core, and then it is getting linked with the secondary winding. Whenever the flux gets linked with the secondary winding, depending upon number of turns here, a voltage will be induced induced here, right? So this is how a normal transformer is going to work here. Okay, तो समझ में आया ट्रांसफार्मर कैसे काम कर रहा है?
Yes, sir.
So what the next thing we need to do is now we have to study what is differential transformer. So I have explained you normal operation of the transformers, but now whenever we are going to discuss about the differential transformer, so how this differential transformer is going to work here. So now the only difference in the normal transformer, differential transformer is here the secondary winding you are having in the normal transformer is divided into two parts, and like you have cutted the secondary winding and you have divided that into two parts, like the upper one and the lower one. Okay, and then you are connected these two windings in such a way that the EMF induced in this and the EMF induced in this will be equal. Okay, that means let us consider in this coil you are having the 5 volts voltage, and here also you are going to have the 5 volt voltage. So these two 5 volts will be equal. That means the voltage induced in the this secondary coil and by this secondary one and this secondary coil secondary 2 will be equal. And apart from that, what we had done the connection in such a way that these two voltages are phase opposition. That means let us consider the voltage in the primary this secondary coil. Okay, V is plus 5 volts, so the voltage in this secondary coil will be minus 5 volts. So if you are going to take the complete voltage, the complete output voltage will be 0, right? So the only difference in the differential transformer is the secondary voltage that you are getting at the output, that means the voltage that you are getting here will be the difference of the EMF induced in the first part of your secondary winding and induced in the second part of your secondary winding. Okay, so the only difference here in the differential transformer is 1 minute. Okay. So the only difference in the secondary differential transformer is here the secondary winding has been divided into two parts, and the two parts are divided in such a way that the EMF induced in the first part and the EMF induced in the second part will be equal. Okay, and apart from that, both this EMF will be phase opposition. That means if you are going to take the output voltage will be zero here. Okay, so now have you understood this?
Yes, sir.
So this is the first initial thing happening here. Okay, what the initial thing happening here, whenever we are going to excite our primary winding, okay, we are going to give some voltage in our primary winding. So this voltage produces a flux, and this flux will travel via this core and it links with the both the secondary windings. It will link this with this secondary winding and it will also link with this secondary winding. So EMF will be induced here and also induced here. Okay, but what the thing happens here is the two EMFs are opposition, so the overall output voltage will be zero. Okay, the initial thing happening here. Here I am not moving this core, so just I am giving my input voltage and I am getting my output voltage at 0 volts because the both secondary windings are connected in phase opposition. Okay, so now how it is acting as a transducer. Okay, so I had said at the starting that the LVDT is going to convert the displacement into electrical voltage, right? So the transduction operation here is it has to convert the displacement into electrical voltage, or it has to convert the change in displacement into electrical voltage, right? So how it is going to happen? So let us see how it is going to happen. So initially I had excited this primary winding, so I am getting the output voltage at 0 here. Okay, so now let us consider this diaphragm is moving. Okay, let us consider this diaphragm is moving downward direction. Okay, whenever this diaphragm is moving in downward direction, this will move this movable core also in downward direction, right? So whenever this movable core will move downward direction, as you can see initially it is exactly in the middle, and it is able to transfer the flux from the core to this winding and this winding, right? So because of that the both the EMFs are equal and the output voltage is zero. But whenever this core moves downwards because of the movement in this diaphragm, so what happens, so this core will be aligned more in this with this coil, and it will be aligned less with this coil, right? So because of that the EMF induced here will be less and the EMF induced here will be more. So whenever you are going to make the difference, so you are not going to get the zero, so you are going to get the some value, right? You are going to get some value because the EMF induced in both the coils are not equal, because it is because not equal because the core has been moved downwards. So as the core moved downwards, so the magnetic linkage, as I said with you that initially when the core is at the middle, the flux, magnetic flux linking with the primary, this secondary one and linking with the secondary two are equal because of the voltage is equal and output voltage is equal, right? But whenever you are going to consider our case one, when we move this one downwards, so what happens, this core is not in front of this core, the secondary winding, right? It is moving downwards. Because of that, as I said, that the flux is going to travel via this core, and as this core is not in touch with the secondary winding, so less flux will get linked with the secondary one and more flux will get linked with the secondary two. So there will be no voltage balance here, and because of that there will be some voltage at the output voltage, right? So in this way, but as you are changing the displacement here, as you are moving this, so here my output voltage is getting varied. So you can see clearly here that a transduction is happening here, right? The displacement is changed here. So what is happening here, my output voltage is changing here, right? So let us consider the second case here. So in the second case, let us consider that this time the core is moving upward, that means the diaphragm is moving upward. So now what happens, the core will be less in front of this and will be more in front of this. That means more flux will link with the secondary one and less flux will link with the secondary two. So again there will be voltage imbalance, again there will be voltage. But if the in the first case, if the voltage difference here we are getting is positive, so in the second case the voltage here we are going to get will be negative, right? So in this way you can clearly see here, when I'm moving my diaphragm, so my core is getting displaced, and my core is getting displaced, my output voltage is getting varied. So the displacement here is getting converted into voltage here. Okay, so समझ में आया आपको? चलिए जो बोला उनका सही से सुनाई तो नहीं दिया। चलिए तो समझ में आ गया ना। सो यहाँ जस्ट क्या हो रहा है कि द बिकॉज ऑफ द मूवमेंट इन द कोर द फ्लक्स लिंकिंग गेटिंग वेरीड एंड व्हेन द फ्लक्स लिंकिंग गेट वेरीड द EMF induced in the both the two parts of secondary winding will be different, and because of that unbalance is getting happen, and because of that output voltage is different, right? That means because of displacement the output voltage is getting varied here. Okay, so this is how the LVDT is going to work here. Okay, so I think you are able to understand this. So let us move into the second part. So that is our strain gauge. Okay, so normally what the strain gauge is here means the strain gauge will be a piece of wire. Okay, and the basic function of the piece of strain gauge here is whenever the displacement of the wire. Okay, whenever wire is elongated or whenever the wire is compressed, so what happens, the resistance of the wire is getting varied. Okay, so this is how the strain gauge is normally, the strain gauge is going to vary. That means here the length or change in displacement of the wire. What that means, the length of the wire. Okay, whenever you are going to apply the pressure on the wire, so the wire will get elongated, and whenever you are going to remove, the wire will get compressed. So the here the basic function of strain gauge is to convert the pressure into the voltage, and that is acquired by using a resistor. Okay, because the length of the resistor is going to vary here. Okay, so this is one type of strain gauge here. So we can call this as an unbounded strain gauge. Okay, if you go through the textbook and whenever you are going to study about the strain gauge, so there you can clearly see that you are going to have two strain gauges. Okay, one will be bounded strain gauge and other will be unbounded strain gauge. Okay, so how it is going to work. Okay, so you can see here I am having four coils here. One, this will be my coil A, this will be my coil B, or you can call it as the wire B, and this will be my wire C, and this will be my wire D. Okay, and I am having two frames, and this frame will be my fixed frame, and this frame will be my mobile frame here. Okay, and what I am doing here is I am connecting my mobile frame, which is able to move here, to an diaphragm here. Okay, so whenever I apply the pressure on this diaphragm, so this diaphragm is going to move, and whenever this diaphragm is going to move, so this moving mobile frame is going to move here. Okay, so now let us see how it is going to work. Okay, so let us see how it is going to work. So let us consider now I am applying my pressure in this direction. Okay. So I had applied my pressure in this direction. Whenever I had applied my pressure in this direction, so it's basic that this diaphragm is going to move in this direction, right? So whenever this diaphragm is going to move in this direction, so this mobile arm, this particular mobile frame will move in this direction, right? So whenever this mobile frame move in this direction, so the length. because you can clearly see here one end of the B is connected to the fixed frame, other end is connected to mobile. Similarly, one end of the C is connected to fixed frame and other one is connected to the mobile frame, right? And similarly happens with the A and D. Whenever whenever my mobile frame moves in this direction, so this as the one end of the C is connected to the mobile frame, so this will pull this wire, right? This is going to pull this wire here. So the length of the C will get elongated and the length of the B also will get elongated, right? And if you see the A and D, so the length of the A will get reduced and length of the D will also get reduced, right? So you can see here clearly whenever I am applying the pressure in this direction, so my diaphragm is going to move in this direction. So this will move my frame in this direction. Whenever my frame moves in this direction, so the B and C, the length of the B and C will elongate, right? You can see here because it is fixed and it is pulling this B and C in this direction. So you can clearly see here the length of the B and C will increase, and you can see here when this moves in this direction, the length of the D and A will get reduced. Okay, so as you can see that two of my wires length are getting increased and two wires length are getting compressed, decreased, right? So after that, at the background, that means this is the upper part which you can clearly see here. So at the background, if you see, this is our strain gauge, right? So if you see here, so the strain gauge is going to connect like this. Okay, the A wire will be something like this will be A wire, this will be B wire, this will be C wire, and this will be D wire, right? So initially what happens, initially when no pressure, like whenever we have not applied any pressure here, so everyone will be in one length, right? So when all are having the same length, so all resistance will be same, and because of that you can call it as a bridge here. So what happens, this resistance is same, this resistance is same, this resistance is same, so all the resistance are same here. So what happens, um, like you can call it as a V-stone bridge here. So we are applying our excitation. So we are going to observe our apply excitation in between those two junctions, and if we measure the voltage in between these two junctions, this junction and this junction, if you are going to measure the voltage in between these two junctions, so the voltage, or you can call it as a current, there will be zero because all the resistors are going to have equal resistance. So the voltage here will be same and there will be no any deflection here. Okay, so normally in Keystone bridge excitation will be given, the excitation will be given between this junction and this section. Okay, so initially when no pressure is applied on the strain gauge, so all the resistors will be equal, and because of this balance, bridge will be in balanced condition, so there will be no voltage. Okay, so normally what happens in the B-stone bridge, I will explain you shortly. Okay, so the B-stone bridge is going to have four arms. Okay, like you can see here, arm 1, arm 2, arm 3 and arm 4. Okay, so in between two arms, like between this junction and this junction, a voltage, DC voltage will be applied. If it is a DC bridge, a DC voltage will be applied. If it is AC bridge, AC voltage will be applied. So let us consider this DC bridge. Okay, so between two junctions voltage will be applied and deflection will be measured between other two junctions. Okay, so if all resistance are equal here, so what happens, the bridge will be balanced, and because of that there will be no voltage drop anywhere, and then what happens, there will be no deflection between these two junctions. Okay, we are not going to measure in between these two junctions. Okay, because we had applied a voltage, I had written here clearly, I had applied excitation in between these two voltages junctions, so there will be no deflection there. So you have to measure the deflection between these two. Okay, whenever you are going to measure the deflection between these two, so the deflection, there will be no deflection because the bridge is balanced here. Okay, so now let us consider the first case. So my first case here is I am applying a pressure in this
एक्सक्यूज
direction.
मी सर.
हाँ,
सर वो बैलेंस कैसे हुआ एक बार फिर से बताना सर.
ठीक 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 बता रहा हूँ. देखिए, so what's happening initially? Okay, so initially what's happening, so remember that whenever we are going to have any resistance bridge, so the bridge is going to have four junctions, four arms. Okay, so this will be my arm 1, this will be my arm 2, this will be my arm 3, numbering will be different, and this will be my arm 4. Okay, so now what happens, so initially when nothing, we had done nothing with the bridge, so all the resistance will be equal. Okay, whenever all the resistance will be equal, so the voltage drop, the voltage drop here, the voltage drop here, the voltage drop here, the voltage drop here will be same. so there will be no volt deflection here. If you are going to measure, if you are going to place a voltmeter in between these two junctions, between this junction and this junction, so you are not going to get any voltage because all the resistance are equal, and as the voltage drop is same, so all are going to get cancelled, and the deflection will, there will be no deflection, and the bridge will be called as the balanced bridge because all the resistance are same, and because of that the voltage drop is
Sir,
balanced.
sir, what about RX and RT?
RX and RT are just given to compensate. Actually, what happens? So as these are the resistors here, okay. As these are the resistors here, so what happens here means because of some temperature fluctuations here, okay. So if there is any fluctuations in the temperature, so the resistance values will get changed, okay. As I said that initially all the resistance values should be same, then only the bridge will be balanced and you are not going to get any deflection at the outside. But as I'm not doing anything, but because of the variation in the surrounding temperature, so if they are, because as you know that the resistors are going to a positive temperature coefficient, that means if the temperature increases, the resistance is going to increase. So whenever the temperature increases, the resistance of all the different resistors is going to increase or decrease, like and because of that unbalance will occur, and because of that voltage is going to get occur here. But I have not, do nothing, but the voltage is getting occurred here because of change in the temperature. So to compensate the change in temperature effect, because we are getting some deflection because of we are not applying the voltage, because we are getting the deflection here because of temperature variations around the surrounding, right? So to compensate that, we are using this RT and RX. Okay. So normally RX is a unknown resistor
Yes,
here.
sir. Yes, sir. Understood now.
What? You got repeat.
हाँ सर
Just can you repeat again because I am getting your
समझ गए
voice.
समझ गए
समझ गए ना? To compensate the temperature effect, we are adding the RT and RX here. Okay.
सर
हम्म, आपका आवाज़ कट रहा है यार.
समझ
आप अगर डाउट है तो एक बार चैट बॉक्स में पोस्ट करिए ताकि मैं देख लूँगा, ठीक है, क्योंकि पता नहीं आपका आवाज़ कट रहा है मुझे. सो समझ गए हैं ना?
यस सर समझ गए
ठीक ठीक ठीक. तो मैं आगे बढ़ सकता हूँ ना. तो what happens initially, all the resistance are equal here, and because of that the bridge is balanced and you are not going to get any deflection here. The additional resistors that you can see here are for temperature compensation here, okay. So now when I am applying my pressure in this direction, so length of the two resistors B and C are increasing and length of the A and D are decreasing. So because of that, whenever the length increases for a wire, so the resistance is going to increase because resistance and length will be directly proportional here, okay. So the B and C, I don't know where the B and C has been placed. So where the B and C are placed, the resistance will increase, and like let us consider B is placed here and C is placed here. So here and here the resistance will get very increased, and A and D are here, so these two resistance will get decreased. So you are going to get some voltage here, right? And similarly, if you are applying the um, pressure in this direction, okay. So what happens? This way, this one is what happens now. This movable arm is going to move in this direction, okay. So now A and D length will increase and B and C length will decrease. Again the unbalance will occur and here the voltage will come. So in this way, what's happening? The pressure, because of the pressure the movable arm is moving, and because of the moving of the movable arm, two device resistance are increasing and two device resistance are decreasing, right? And in this way, whenever the resistance are increasing and decreasing, the output is getting, the bridge is getting unbalanced and you are getting some output voltage here. So here you can clearly see that because of the variation in the input pressure, so you can see here my output excitation is going to vary here, okay. तो समझ में आया?
हाँ जी सर आ गया
So this is how the strain gauge, and this strain gauge is called as an unbounded strain gauge. Okay. So now let us move into the second one. Okay. Bounded strain gauge. There is another one about this, but I am not discussing that. So let us discuss this one. Okay. So as you can see here, we are using the resistors at the in the strain gauge for measuring the change in present here. Now this is made by using semiconductors here. Okay, so many of you know what are semiconductors, and some of you may know or may not know the semiconductors. So normally the semiconductors are designed by using the silicon, germanium like semiconductor materials, right? So nowadays whatever you are going to use, what are the electronic devices that we are having at present, all are designed by using the semiconductors, right? So this is one of the advanced type of the strain gauge where the semiconductor materials may be used for designing the strain gauge here. Okay, so what you can see here. So I think some of you may know the P type and N type conductors. Okay, so if you are taking the pure semiconductor, okay, like you are taking a silicon or you are taking a germanium, right? So the silicon or germanium which you are going to take, it will be a pure semiconductor, right? And what we do, we will add the impurities, right? We may add the trivalent impurity or we may add the pentavalent impurity, right? Remember one thing, if I say a pure semiconductor, so it is going to have four, okay, it is going to have exactly four. The semiconductor materials are those materials in my atomic periodic table which are having four atoms at their outermost orbit. Okay, so what we'll do normally, so what what we are going to get, uh,
आवाज बहुत कट रहा है आपका।
सुनाई दे रहा है आपको?
अब दे रहा है।
अब ठीक है, अभी भी कट रहा है?
अब ठीक है।
ओके ओके ओके। मैं बाहर हूँ, सिग्नल का इशू है रूम में। ओके, so what happens, uh, so normally whatever the devices you are going to design, they are maybe used by using semiconductors, right? So we will take first a pure semiconductor and then we use it to add some, okay, we may add trivalent or we may add the pentavalent purity. So like if you take any material which is having three valence electrons, then it will be called as a trivalent. And if you take any metal which is having five valence electrons, then you call it as a pentavalent. What we will do is, I mean, just explaining from basics because those who don't know, they can also, and those also know, they can brush up their knowledge. Okay, so we will take silicon, okay, and sorry, we will take a silicon and we are going to add some impurity. Okay, this process, okay, add impurity to a silicon, then this material is going to call as p type. Okay, and if you are again taking some silicon here, okay, then now you are adding a pentavalent impurity to this, then you are going to get a n type material. So another one will be a pentavalent. Okay, so 1 minute. What we are going to do here is go to the same thing. Okay, um, um, so what we are going to do is this lab,
सर आवाज नहीं आ रही सर,
exactly.
रुक
Okay, and then एकदम नहीं आ रही है।
बहुत ज्यादा रुक रही सर।
मैं सोचा नहीं तो मैं फ़ोन से प्रेजेंट करूँगा, ठीक है। प्रेजेंट कर दूँगा। ओके, आई एम लैगिंग राइट, बट इन प्लेन वीडियोस फ़ोन से